today we're going to talk about simple probability, just like what you learned in Algebra 1, and we're going to learn to apply that to geometric probability, and then hopefully there'll be a couple minutes at the end, and we're going to go over permutations and combinations, not because it has a ton to do with this, but because it's going to be on the OGT, and you haven't had it for a year, so I just want to make sure that you remember what that is and how to type in your calculator. Because it's really easy if you know how to type in your calculator. So I don't want you to miss that just because. All right. So if you remember back to Algebra 1, probability is the things you want to happen over all the possible things that could happen. Okay? So famously rolling a dice. What if I wanted to find the probability of rolling a 4? How many good things could happen? Okay, let's say somebody walks up to me and says, if you roll a 4, I'll give you $1 million. What would be, how many good things could happen? 1. I could roll a 4, right? How many possible things could happen? 6. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. So my probability of rolling a 4 is one thing I want to happen over 6 things that could happen. So my probability of rolling a 4 is 1 out of 6. Okay? And you write it with the thing you're trying to take the probability of inside parentheses with a P on the outside. So the notation for probability looks like that. Okay? So it's just one of those things that's easy unless you don't know what that means, and then the problem becomes really hard. Okay? So let's say I'm trying to find the probability of rolling an even number. Okay? These are my old rolling. These are my old there we go. These are my old algebra notes. We did this. I just wanted to show you. Okay. So if I want to find the probability of rolling an even number, how many good things can happen? 3, 2, 4, and 6. How many possible things can happen? 6. So my probability of rolling an even number is 1/2. Right? So if I roll the dice 100 times, how many times would I expect to get an even number? 50 times. Right? Because half of the 100. If I rolled it 200 times, 100. And if I rolled it 1,000 times, 500. Right? Now, chances are it won't be exact, but the more you do, the closer it gets to be exactly half. Like if I rolled it 1 billion times, chances are I'd be really close to 500 million even numbers. But if I just rolled it 50 times, it probably wouldn't be close to 25. It'd be more like 17, 30. Probability of you rolling dice. 1 billion. Yeah, I can't even imagine how long that would take. All right. So that's basic probability. Geometric probability does the same thing, but it does it in terms of shapes. Right? We're still going to do what we want to happen over everything that could happen. All right, so let's say this was a mat laying on the floor, and I threw a penny up in the air and it landed on the mat. So it could land, here, 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 here. It could land anywhere on the mat. If the mat is 12 by 8 and the square is 6 by 6, the probability of it landing on this area that's orange, the square, would be, the good thing that happened would be it landed in the square. How would we represent the area of the square? 36. Right, 6 times 6, 36 square inches. Let's say it's inches. Okay? So what we want to happen would be happening in that 36 square inches. But how many possible places could it land? Yeah, there's 96 square inches total on the mat, right? 12 times 8. Okay? So my probability of tossing the coin and having it land in the orange area is reduced down 3 over 8. So that means, theoretically, if I threw the coin up 8 times and let it fall, how many times would it land in the orange? 3. Okay?
About where you threw it? You throw it above the square.
I mean, you're going to have some independence issue there. Like if I was trying to hit the orange, that'd be different than if I just randomly.
Eyes closed, back towards the net.
Right. Okay. And then probability can apply to all kinds of geometric situations. Like a line. We can't get an area of a line, right? Because it only has one dimension. But let's say, pretend like this line was like a railroad track. And I want to know the probability that the train would stop between B and C. Well, I would to find that probability, I would find the length of BC over all the possible places it could stop, which is the length of AD. Okay? Same theory, but just applied in a different way. Does that make sense? So the probability of the train stopping in this area here would be the length of that over the length of the whole thing. To put some actual problems to it. So the probability of it stopping in BC would be 5 out of 12, because the whole thing is 12. Okay? And then another couple probability things I wanted to remind you of. If two events are independent of each other, like two coin flips, the first, does it matter what I flip the first time? Will that affect what I flip the second time? If I flip, I get a heads. Because what does that mean about the next flip? Yeah, it could be anything. It could be heads or tails. So we call those independent events. One doesn't affect the other. Okay? When you're trying to find the probability of two independent events, you multiply. When you're trying to find the probability of two dependent events, like the train stopping in two different areas would be dependent, because if it stopped here, will it stop here? No, it's already stopped. So they are dependent, they're not independent. The fact that it stopped here will affect whether it stopped here or not. When you have two dependent events like that, you add them. Okay? So the probability of it stopping on AB is 4 out of 12. The probability of it stopping on CD is 3 out of 12. So the probability of it stopping either place is 7 out of 12. Make sense?
Bad, you have to have the same denominator.
Yep. Okay? And the other one is, what's the probability that the train does not stop on CD? Does not.
9 out of 12. Or 9 out of 9.
Yeah, 9 out of 12. If it doesn't stop on CD, isn't another way to say that? What's the probability that it does stop on A, B, or B, C? So it would be 4 and 5, 9 out of 12. Okay? Make sense? Coming back to kind of. Alright, same thing, applying the same principle to angles. If I told you this was a 50-degree angle, and I said, what's the probability that I would spin a spinner and it would land inside this 50 degrees, how would I write that as a probability? Right? All the way around the circle is 360. So it's 50 over 360. But I want to happen over total positive. Okay? The area one works just like the orange square. I won't take time to do that because I'm getting close. Alright? So, near the end of when I was working in Washington, I was doing some contractor work for the Secret Service. And that was when President Bush um, retired, was no longer president. Um, he lost his election. So, you know how they say, President Bush, you're not looking at, you're a retired president. What do you do now? And the sports people always say, I'm going to Disney World. Well, President Bush said, I want to skydive. I've always wanted to. So our 73-year-old president decided he wanted to skydive. Well, I happened to be doing some work over at Secret Service. That threw them into a total tizzy because think about trying to provide security for someone who is up in the air coming down. Like, you don't know where they're going to land. You don't know, what's going on there. So this was an actual application of how they use geometric probability. Okay, they, when you first learn to skydive, I don't know if you guys have ever had anything to do with this. You don't skydive by yourself the very first time. You're usually strapped to someone who does it all the time and knows when to pull the cord, so you don't just. And so they called that guy and they said, okay, given the wind conditions, given the height of the plane and the squeakiness of the door, everything involved, give us the total area that is possible for you guys to land in. All right? And now it wasn't this pretty, it wasn't quite a rectangle, but for our purposes, it'll be a rectangle. So he said, okay, this is given getting blown off course or jumping out a little bit late or whatever. This is the total possible area we're going to land in. Okay? But I'm working very hard and I'm going to make sure that we land in this square, which is good because you don't want the president to land in all those trees, right? So the Secret Service had to figure out if they needed, how many men they needed out here, how many men they needed in here. All right. So the first thing they did was figure out the probability that that guy's going to land right there. So you did that. Okay. So how would I figure out that probability? What would be on top? The area of the square, which is 21 by 18, which is what? 378. What's the bottom? Right, 28 times 35. Okay, which reduces down to 27 over 70. Okay, so now think about that. If you were on this Secret Service detail, would you feel comfortable just putting some guys right here? Is that a good enough probability that you don't feel like you have to put people around here? No, I mean that's less than half, isn't it? So, oh yeah, he seriously started skydive. He did go this day because it would have cost so much. The probability was so low, and they would have had to allocate men, so many men that it got too expensive. So they had to postpone it into another day when it was, better weather, better whatever. I'm not sure of all the details, but yeah, he really did.